Hey everyone, this is going to be a little of a different episode where I'm going to be going over the basics of foundation engineering drawings. I'm going to be showing you some of my resources, and you will be getting a slight look ahead at to what we're going to be building in the next foundation episode. So let's jump on in. In this initial section, I'm going to show you the engineering drawings for the foundation. I wanted to start here because I know when I was a beginner, and this might be kind of basic for people that are aware of how these drawings work, but I know, at least from my perspective, it would have been very useful for someone or some video to show me how to read these diagrams. Because the very first time I looked at them, they were like, oh, what the heck, what? I have no idea what's going on. So I believe the general process, if you're going to be doing this, is to anchor to something that you know about the house. So for example, let's begin by this top of basement slab that's set at 90 feet, 10 inches and a quarter. Then we have another top of basement slab. Then we have a top of wall, and whatnot. So these are dimensions that typically architects like to go by. So typically architects go by the 100 mark. And by the 100 mark, I mean in your permit package or your house paperwork diagrams, you will have a view from the north, east, west of the house. And you will see these references where you see the 100-foot mark. In our case, as I just mentioned, there's the 90-foot, 10 inches and a quarter. So this will be the top of slab. So this will be the floor of the bottom floor. Then we have the 100-foot mark that will be the floor of the entrance, and so on and so forth. So my suggestion in general is to anchor to something that you know. And it is sometimes easier to zoom out and look at this more basic views before digging into the foundation. So once you have your heights understood to some extent, you will notice that this view is actually being seen from the top. And there are two kind of dimensions that you're looking at when you're looking at this diagram. So for example, here you can see the contour of the house, the walls of the foundation. And then we have these dotted lines that represent the footings of the foundation. So here we have some basic nomenclature for definition. So for example, TOW will be top of wall, BOW will be bottom of wall, TO ledge, top of footing, bottom of footing, and so on and so forth. So with that said, you will see that we have a big retainer wall here, and we have the contour of a footing. Similarly, you go around and you will notice that the top of wall here will be 99 feet, 9 inches and 3/4. And note how this is not exactly 100. I mentioned that this was the top of the floor, but the reason this is not 100 is because it's accounting for the width of the subfloor. In this case, 3/4 inch, although in our case we will end up using a 1 1/8 inch thick subfloor. But that's giving you a perspective of what's going on. And then when you dig deeper, you will notice that the top of footings will be 90 feet, 3 1/4 inches. And so this is actually lower than the top of slab that will be 10 inches and a quarter. So that's effectively 7-inch difference from the top of these footings to the actual top of the slab. And the reason for that is because the slab will be 4 inches by requirement. And we get an additional 3 inches of insulation to this set assembly for the slab. And you will be able to see this better in a little bit when I show you. So once I got my bearings on the drawing to some extent and the heights and whatnot, I actually went on to Blender and began doing a 3D drawing on it. So for example, that was the top view. So now I can actually show you the top of wall, the top of footing, the bottom of footing, and whatnot. Because this is in the mountain and we have stepped footings. It was difficult for me to visualize from the 2D drawing how these footings were going to look, but here it is a little bit easier to see what the drawings mean. So for example, if we look at this footing, there's a step, and you will notice here on the diagram that there is a step. So for example, there's the top of footing at 91 feet 10 inches, and then the line ends here. And then if you look over here, there's the top of footing, and that's at 90 feet flat. So that's effectively what you can see here represented in 3D. This also allowed me many other things, such as defining the sleeves for different for the plumbing and electricity and that kind of stuff. So it has been extraordinarily useful. Another thing I want to show you is we also decided to define the threaded rods and the anchor bolts. In order to better show you how we ended up defining the J-bolts and the anchor bolts that go into the foundation, it is kind of important to go into the framing diagrams of the engineering drawings. And the engineer provides a brace wall panel schedule that defines the different ways of strapping the house down to the foundation. So let's say, for example, here we have a P4. And effectively what that means is we have an anchor bolt that connects to an HUD Simpson holder, and it grabs the foundation and it embeds onto the foundation. So you can go around the house and do all those definitions. This house actually has some metal, but I will not be going through this at this moment. I will probably create a video when we get deeper into framing. So in that particular P4 bracing schedule, you will notice we have these anchor bolts that actually go into the wall. And you can actually see here how deep they actually go. They actually embed onto the wall, I believe, 14 inches, and they stick out like 10 inches. So they end up attaching to the wall. And you can also see how I define the different J-bolts along the foundation. And the intent is to mark them such that we don't have to drill onto the foundation, and this will be embedded at pour time of the foundation. So you may wonder, how did you figure out where these different anchors and J-bolts go? And I figured out by having to do the framing of the house. So here's the example now with the framing created. Like I said, I will go through this in a future video more in detail, but you can actually see the Simpson hold downs and how they operate against while holding the house down to the foundation. So for example, if we start removing the framing, you will begin to see we have our bottom plates and how the different anchor bolts stick out. So by doing the framing, I am able to determine the exact location of the different anchor bolts. Similarly, you see we have the metal. So now I remove, but you can see the plates. We have our top plates, our bottom plates. And now you can see the subfloor and how the different J-bolts stick out through them, as well as our metal plates for the different metal beams. So in summary, in order for me to be able to determine the location of the different J-bolts, I actually had to build a framing. And that's why doing this 3D design was critical in order to be able to do that. So now that I've shown you how I determined the location of the different J-bolts and the anchor bolts, let me show you a couple details for building the stepped footings. This is something I found interesting because from all videos I looked around, most people build on flat ground, so they don't typically have stepped footings. So the first detail for a stepped footing is kind of how I have them on Blender. The footing comes in, it breaks, and then the footing continues at the bottom, and they don't interconnect through rebar. However, they do interconnect through rebar along the stem walls. The other kind of footing that we have, and we will actually be using both of them, and you will see that on the next episode of the foundation pour. There's the footing where it is continuous, so there's rebar and then it waterfalls onto the next footing, and that allows a continuous attachment of the footing, and this may be for applications where greater strength is desired. And then similarly they attach through the stem walls. So for example here, this would be a non-continuous stepped footing, so the footing comes in, the rebar, but the rebar stops here and it does not interconnect to the bottom footing. However, the rebar does connect internally, like at 45 degrees and horizontally along the stem walls. In the next episode, you will also see how the engineer requested to have these two footings waterfalled together, and that would be the other detail of the footing. So that's where the rebar runs from one footing and then waterfalls onto the next one, and then we effectively can have a stepped continuous footing. So finally, before moving on, I want to quickly show you some details about the wall structures. So for example, here we have dowels, so you can see the rebar, number 5 rebar that connects at the bottom of the footing, and then there's dowels that get embedded onto the wall, and then we have a rebar along the wall, so we have here horizontal along the wall, and then here vertical, and there's a space of 2.5 inches. I don't necessarily want to dwell too much on this because there are many different walls and many different details, so let me know if you want me to go through that in the future. But it's important to note the different sizes of the rebar. Knowing that we are actually officially begun building the foundation, I can tell you that the engineer came back and he made us rework some of these dowels because they were not rebar number 6 rather than 5. So yeah, just as a general contractor, I would suggest pay very close attention at the definition from the engineer, and that way you will save yourself some time. To finish up, I want to talk a little bit about the concrete mixture that I'm requesting the subcontractor to provide. They have their default mixtures in general, but I did request to get macrofiber mesh added to the mixture, and the reason for that is because it helps minimize cracks to some extent. It doesn't make the concrete necessarily stronger, but it does help against the expansion of cracks. The thing about concrete is that it's very good in compression, but not so great in tension. So the rebar is there to help the concrete against tension, but obviously there's no rebar everywhere. So by adding the macrofiber reinforcement, it's kind of like having a bunch of little rebars all over the place that help the concrete against tension in different circumstances. So I want to show you some of my references. So for example, there's this guy, Tyler Ley. He's a professor somewhere in the South in a university. And I highly recommend you reviewing these videos, and I will put the links in the description below. He talks about fiber reinforcement and how much better it makes concrete. Here's a video of an example of a jackhammer against fiber mesh reinforced concrete versus a non-fiber mesh reinforced concrete. And one final topic about concrete in general is concrete has the capability of actually exploding when there's a really hot fire. And that may be due to maybe water trapped inside the concrete. Maybe it boils and then it explodes. And actually, there are videos for this, and I highly recommend you checking this video out. It's also in the description below. I hope you enjoyed this episode. It was a little bit different. If there is something in particular you would like me to go over, or more detail, please comment below. The best way you can support us is by liking and subscribing to our channel, and see you in the next episode. Bye.